So 2 years ago, Metrohm USA decided to recognize the achievements of the budding scientists out there and really promote academic interests, especially in the field of chemistry. We opened this up to all the students in the United States of America. It doesn't have to be using Metrohm equipment. It doesn't have to be using Metrohm technologies. What does require is novel research on some methodology that we would prefer to see some titration, some ion chromatography, some electrochemistry, something infrared, something that's somewhat related. But the real key is novel research from an up-and-coming scientist. Last year, our first winner was Matthew Dawson from the University of California in Irvine. He was doing predicting gas particle formations and growth from gas phase precursors. And Matthew's not here with us today, but we have another recipient to announce. So I'd like to have Ed and Kai please come to the stage first. This year's winner is Ms. Linghong Zhang from the University of Wisconsin at Madison. So would you please come up and join us? We will be presenting her with a $10,000 check in recognition of her work. She earned a bachelor's degree of engineering in China, where she developed methods for the metallization of protein-based membranes. She's also done a lot of synthesis of nanoflakes for photocatalysis and a lot of different syntheses. She's continuing her research, her PhD work at the University of Madison in Hamer's group, where she studies the modification of molecular catalysts. And what's really interesting is she's working with a lot of diamond base here. So we're pleased to introduce the soon-to-be, hopefully, Dr. Zhang. So, rather than subject you to reading the abstract, I'm going to ask Linghong to give us a short overview of her work. Thank you very much.
I'm Linghong. I'm from University of Wisconsin-Madison. And it's my great honor today to be here and to get this award, a Young Chemist Award from Metrohm. And also, of course, I'm really grateful for the big check. It is definitely the biggest check that I've ever received so far. So thank you very much for it. I was told I have 5 minutes, so I prepared several slides to tell you a little bit about my work. So my research focus is CO2 reduction, and which is about converting CO2 to chemical fuels. To chemical fuels, as we all know, the atmospheric CO2 concentration has been going up over the past several decades, and this has caused increasing concerns about its impact on global warming and climate change. It has also triggered a lot of interest in investigating the possibility of converting CO2 back to something useful, such as different kind of chemical fuels. However, there are a lot of challenges. For example, it requires high energy, CO2 reduction requires high energy input, and the reduction products can be too diverse to be efficiently used. That's why people are always looking for better catalysts and better catalytic systems. So for the system that we developed, this is actually a collaboration between my group and Professor John Barrett's group at UW-Madison. We attached cobalt porphyrin, which is a molecular catalyst, onto diamond surface through covalent linkage and use it for the application of CO2 reduction. What is good about molecular catalysts is that they not only lower the activation energy of CO2 reduction, they also have a better selectivity towards certain reduction products. And we choose diamond to be the platform, electrochemical platform, is because diamond is very stable, it is chemically inert, and it has a very large electrochemical window to do this kind of application. And also, I guess a lot of you might think diamond is very expensive, but actually it's fairly inexpensive. It's like $70 a piece, and then you can always reuse them. So it's pretty good. So for this kind of heterogeneous system, they also are very stable. It requires minimum amount of catalyst loading. The electron transfer between the molecular catalyst and the electrode can be very fast. And also there's no need to separate product and the catalyst. So as soon as we made the product, we made the sample, we put it into a 3-electrode system for catalytic behavior tests in acetylnitrile. So this is the result. For cobalt porphyrin attached diamond sample, we see a difference in current between our CO2 saturated system and argon saturated system. And this difference in current is caused by CO2 catalytic reduction. And for comparison, we also did we also made zinc porphyrin attached diamond sample, and as you can see, there's no difference in current here. So this means our surface attached cobalt porphyrin is catalytically active. Furthermore, we went on to do some product detection and through Fourier transform infrared spectroscopy. Because we use 0.5 group number as the resolution, the rotational vibrational lines of carbon monoxide are resolved. So you can see like these little spikes here are the signals from carbon monoxide. And this pattern matches very well with the experimental standard that we did FTIR on. And also it matches pretty well with the calculated signal from HyTran database. So this is what I want to tell you about my research. At last, I'd like to thank Metrohm again for this great opportunity to present my work, and also the great to present my work, and then thank you for the award. And also I'd like to thank my advisor, my wonderful advisor Bob Hammers, who's also here today. Thank you very much for the support and everything. I'd like to thank my coworkers, Rose Ruther, Shu Yao, and Tim Bertle, and also all Hammers group members, and also my funding from Air Force. Thank you very much for your attention.
Why are you interested in studying CO2 reduction?
I'm interested in CO2 reduction. First of all, it's because of its environmental impact. It's good to be part of the team to solve the CO2 problem like in the world, and it just feels good. And also, I'm very interested in electrochemistry and in catalysis and both photocatalysis and electrocatalysis. So this also falls into my interest. For now, we're still doing like benchtop chemistry. This is just trying to prove that it's just trying to prove that the system works pretty well. In the future, we're gonna try to attach different other catalysts onto the surface of diamond to see how diverse, how general this system can be, and also maybe try to find out how economic it can be in the future to make it maybe work towards more applications. So the take-home message for this research is that we're able to develop this heterogeneous catalytic system to attach a molecular catalyst onto the diamond surface with very minimum loading, and this is pretty robust right now, so we can do CO2 reduction using this system. I'm doing both photocatalysis and electrocatalysis for CO2 reduction. For now, my focus is on photocatalysis, but the future work for me is just to try different, for electrochemistry part, it's just to try different catalysts on this diamond surface.